and also policies and procedures on the security side, data analytics, enterprise data services, here's your databases, learning services, training and development, managed services, tier 1, tier 2, tier 3, as well as system and cloud services, which is your Red Hat, as well as any kind of implementations from Windows, Office 365, other stuff like that too. So with all that said, I would like to introduce a good friend of mine, Jim Garrett. He is the principal solution architect at Red Hat. He will be giving a 30-minute presentation on OpenShift Service Mesh. And then another one of my colleagues and good friends, Tom Lapp, who's our principal consultant and technology lead on DevOps. With that said, Jim, please take it away.
Great. Thanks a lot, Matt. Appreciate you giving me the opportunity to speak, and I appreciate everybody joining us today. As Matt said, my name is Jim Garrett, and I'm a principal solution architect at Red Hat. I've been with Red Hat for almost exactly 4 years. However, prior to Red Hat, I spent over 30 years doing software enterprise architecture and development. And the topic we're going to talk about today is actually a topic very near and dear to my heart, as it directly applies to some of the new things that new solutions we're providing that provide great features for software development. So first thing I want to talk about is what is a service mesh. A service mesh is going to basically give you the ability to take on a responsibility of making service communication resilient to failures by implementing capabilities like retries, timeouts, and circuit breakers. It's also capable of handling evolving infrastructure topologies by handling things like service discovery, adaptive and zone-aware load balancing, and health checking. And since all of the traffic flows through the mesh, operators can control direct traffic explicitly. For example, if you want to deploy a new version of your application, you may want to expose it to only a small fraction, say 1% of live traffic. And that's what Service Mesh is all about. The Service Mesh provides all of these capabilities to your operators with very little or no application code changes or dependencies or intrusions. So for some of these capabilities, there will have to be a minor cooperation with the application code, but we can avoid large, complicated library dependencies. So with the Service Mesh, it doesn't matter what application framework or programming language you've used to build your application. These capabilities are implemented consistently and correctly. And the capabilities that the Service Mesh provides allow our service teams to move quickly, safely, and confidently when implementing and delivering changes to their systems. So let's talk a little bit about how the Service Mesh works. So the Service Mesh provides all of these capabilities to your operators with, again, very little to no application code changes. With the Service Mesh, it doesn't matter what application framework or programming language you've used to build your application. And on this slide, I actually have an example of a shopping cart. This shopping cart could have been developed with any of your modern tools. These could be Java, microservices, these could be Node.js. It could basically be anything that you've incorporated today. And the key with this is with the Service Mesh, we incorporate something called an Envoy proxy, which is going to sit in front of every one of your servers or your services. And just to give you an example of the way that it works, as traffic comes into your cluster, in this case, it's going to be a request for a shopping cart service. The traffic is going to go to the shopping cart service, but it's going to be intercepted by a service proxy. And in this process of being intercepted by the proxy, the traffic is going to be secured with TLS security by default. And when it does that, the certificates for establishing TLS are going to be provided by the authentication node. The Service Mesh determines that the request was initiated by, in this case, a customer that was in North America. And for those customers, they want to route all of the tax requests to a specific version, in other words, version 1.1 of the tax service, which has special calculations for anybody that's in North America. Now, when this happens, there's a couple of other things that can take place. For example, the pilot that controls all of these proxies is used to configure things like routing and security and resilience. We've also got the ability to have metrics that are going to be recorded. So each one of these proxies is going to report metrics back to the system, things like how long did the request take to process and to execute. In addition to that, we have the ability for tracing. Tracing can span all of these proxies, and you can use it later to track how things performed and exactly what path they took. And then, of course, we have this authorization node, which can provide the information back to each one of the pieces. So the authorization node is going to store those certificates. It's going to store everything it needs to enable security and authentication between the different microservices in this mix. And the question is, how do we do that? And the OpenShift answer to that is with the service mesh, and in particular, it's the Istio service mesh. And it's broken down the following. So we've got Istio is going to be at the heart of our solution. It's going to basically consisting of a coordinator for all of the different scheduling of the series of proxy servers, which allow us to control the flow of traffic throughout the system. And then as that traffic happens, we're actually recording information about that traffic, and we are pushing that information and provide like visualization of the metrics to two products called Prometheus and Grafana. In addition to that, we've included a component called Jaeger, which is used to capture requests spanning across multiple services within the mesh. And this gives us the ability to correlate data across the entire chain of events that happen. And then finally, we've got a user interface called Kiali, which is used for visualization of the entire graphs of services that are scheduled within. And basically, you have this loop that happens. Istio definitely controls everything, but you've got these four other products that then provide an eye into exactly what's happening. And when you deploy this as part of OpenShift, this adds a whole nother layer of control to your infrastructure, allowing for additional configurability of your services. So let's take a look at that. Let's take a look at under the hood exactly what's happening. The first one is we hear a lot about microservices architecture. For decades, we've been building monoliths, but we pitch to developers today is to break applications into smaller pieces and decentralize them, as it's going to make it easier to manage individual services. And it provides a way to build, deploy, and scale and manage them separately, possibly by different teams when you break it down into microservices. What this creates is a distributed architecture. When you break the monolith down into all these smaller pieces, you tend to get a lot of them. And as the number increases, the complexity of communication between the services increases as well. So what used to be a function call from one piece of code to another inside of a monolith is now an API call over the network, which means we're relying a lot more on the network than we used to. And by decentralizing these services, we essentially push the complexity that used to be addressed within the application, and we're pushing it outside of the application into these services. So let's take a look at how we can deal with these complexities. So containers, quite honestly, the greatest thing since sliced bread, in my opinion. Containers have simplified the deployment of our services by packaging everything you need for that application and all of its dependencies into an immutable package. In other words, a package that never changes. And that immutable package is independent of the framework. For example, you can create a container using any programming language for that application, which provides a much lighter and easier way to build and to share your code. But with that, we have some challenges we have to solve. For example, configuration. Now on this slide, I talk about one way that configuration is added to these services, and that's by deploying a configuration server, and you add some code into each one of your services to be able to communicate with that configuration server. Along with all of these services, we have service discovery becomes a challenge. We have lots of services and they need to be able to find each other. There is a library out there from Netflix which provides just that. It basically provides a way that you can allow services to discover one another. So again, you can start piecing these different parts of the puzzle together. Something else you're going to need with these services is dynamic routing. And it's used to manage the traffic flow to services, especially if you're running multiple versions of the same service. And again, there's a tool out there called Netflix Zool, which you can write code to and add that into your service. And again, the stack just keeps getting bigger. The next thing you want to handle is fault tolerance. And what we call that, there's actually a pattern called the circuit breaker pattern. And the circuit breaker is like an electrical circuit. The software version allows the flow of the service to be shut off. Basically, the circuit opens in the case where the endpoint is not functioning correctly. So the endpoint may have failed or it may just be slow. But what it represents is a problem. Basically, the problem is the container is not working. And in that case, traffic needs to be routed to other containers, basically by doing some type of load balancing. Another piece that people add to their code once they start developing these microservices is tracing and visibility. Tracing becomes more and more important because requests start to flow between the different services. And as you have more and more services chained together, you need to see what's happening to the responses between those services. So for example, there's a tool out there called Zipkin, where you can add it into your mix and you can write a small piece of code and put it in every one of your services to communicate with Zipkin. Now, this brings up a question. You know, what about your polyglot apps or your existing apps? Well, existing apps, you'd have to change code. You'd have to rewire them to be able to support these various capabilities. And if you're talking about aggregated applications, maybe with multiple languages, you know, your polyglot apps, you have to find other frameworks that might provide similar functionality, or maybe you write it and implement it yourself. And so the question becomes, isn't there a better way? And of course, at Red Hat, we felt that we could absolutely provide a better answer for this in the future. And the answer was to solve more of these challenges externally to the applications. So again, pushing it outside of the application so that you no longer have to write small pieces of code to handle every one of those situations. And the way that we address that is with the service mesh. So we address all of this complexity through a use of the service mesh. So let's see how that works. Again, we have this evolution where on the left side, you can see that when people wrote services, they had to write small pieces of code to handle every one of these situations. But as you move to really more of a service mesh architecture, those things should be transparently extrapolated out of the development of your service. In fact, your service shouldn't have to do anything. It should just automatically be able to leverage these different things that we want to be able to do. So although containers, as we talked about in the beginning, made it simple to build these immutable packages, which are independent of the infrastructure, in order to deploy and manage many of them on top of your infrastructure, you need some sort of orchestration tool. Well, Kubernetes is the #1 de facto standard container orchestration tool, and it deploys its various pieces in something called a pod. And a pod is a lot like a host that can have multiple containers running inside of it. It has a network space, and it can also have storage. Most often, there's usually one container running in a pod, but sometimes you might want to have more than one container. And you'll see one of these cases as we talk about the service mesh. Now with the service mesh, what we do is we create something called a sidecar. A sidecar is nothing more than a container. So basically you're going to have one pod with multiple containers deployed into it. The two containers are going to share the same namespace. They're going to share the network. They're going to share all the resources. And all the containers in the pod are going to share the same life cycle. But the sidecar pattern is often used to enhance an application container. So in Istio, the sidecar pattern is used to add a container called the Envoy proxy. And the Envoy sidecar container can be deployed either manually or automatically injected to your applications inside of that namespace. And when it is injected, all or even just parts of the network traffic to the original container is going to be routed through that proxy. And the Envoy proxy in itself is very simplistic, and it's written in a way so that the performance overhead is very low. So let's talk about this architecture. The architecture of the system is going to be modeled in the same way as most well-designed distributed systems, through the use of some control plane and a data plane. A failure of the control plane does not necessarily cause a failure of the applications in the data plane. It's only the inability to affect state changes. So as such, this allows us to safely perform upgrades, patches, and maintenance on the control plane, knowing that our applications are going to continue to run smoothly. So let's talk about some of the major functionality with the OpenShift Service Mesh. We break it down into 4 categories. We've got fault tolerance, service security, chaos engineering, and dynamic routing. So the first major area of functionality is going to be fault tolerance. And this means the ability to operate even when components of our stack of our applications fail. And we can provide this ability to operate by either doing redirects or retries. So again, if you look at how things were done, for example, circuit breakers, how they were done without Istio. Circuit breakers reflect the need to redirect traffic as part of our environment change or a failure, much in the same way we cut power to parts of our home in an unsafe situation. We can block traffic or redirect it in the case of a failure. In the Netflix model, this requires making changes to each application component, instructing it to request information from the service, such as discovering endpoints to ensure that it knows which endpoint to go to next. You know, think of this basically as a giant switch statement or a case statement that you write in code. In the realm of the OpenShift Service Mesh, we can make this transparent to the services. So you don't have to change your code in any way. Your software developers don't have to know how to write any code to do the circuit breaking. We simply put this Envoy proxy on in front of your service, and OpenShift takes care of the rest. So in this example, if one of the services were to fail, we can actually redirect your requests around the service, allowing us to bypass the failed service and send the request either to a different endpoint or even skip it altogether and maybe go to a different hop. We can also implement timeouts and retries with Istio. Basically, this happens at the network level. Rather than having to hard code those values into each one of your services, which obviously is going to require redeployment, we can actually change the behavior of your service using the Envoy proxy by configuring its timeouts and retries within inside of Istio. Another feature, we can implement rate limiting. This allows us to protect your services against large amounts of request data. For example, if somebody is trying to do a denial of service against your service. So with rate limiting, we can literally throttle the number of requests that hit, or even the percentage of the requests which hit each one of your individual services. Let's talk a little bit about security, as that's also a major piece of functionality that we provide. Security without Istio is kind of interesting because without it, again, you've got to change your code. You may have to write a piece of code that does some type of TLS communication. And depending on the programming language and the framework that you use, implementation could be different across each one of those different tools. Excuse me. But securing the communication with Istio, again, it becomes part of the Envoy proxy. The service code doesn't need to know anything about the TLS communications or the certificates, or that the service only communicates with the local Envoy proxy. Basically, the Envoy proxy takes care of securing all the communications between the services with mutual TLS, and it has the ability to rotate your certificates and your keys for maximum security. So basically, any application using any programming language and any framework could immediately be able to take advantage of your mutual TLS security without any refactoring of your code. We can also control service access. So in this example, we would allow only connections from certain services to access other services. So this ensures that even in the event that, for example, service A in this picture, if service A gets compromised, we can have complete certainty that it would not be able to access resources that it's not authorized to access. So for example, in this picture, service A can only communicate with service B. It does not have the ability to jump out and communicate with service C. And this next point is kind of an interesting one, chaos engineering. I don't know if any of you guys have heard of this or if you've tried doing it. But basically, let me talk about chaos engineering without Istio. And chaos engineering, what it really refers to is failures. What is your code, what's your microservice code going to do when it's communicating with another microservice and that other microservice fails? How do you test that code? How do you know that it's behaving correctly? That's what you call chaos engineering. So with chaos engineering, we have the ability, actually specifically inside of Istio, we have the ability to inject things. We can inject delays that are going to be transparent to those services. So instead of, for example, killing your pod, delaying it, or corrupting packets at a TCP layer, the rationale is that the failures observed by the application layer are the same regardless of the network failure that you may experience. And basically that means more meaningful failures can be injected at the application layer to exercise the resilience of your application. We have two different types of faults that can be injected. We can actually inject delays and we can inject aborts. Obviously delays are a timing failure, mimicking increased network latency or maybe an overloaded upstream service. Aborts are actual crashes, failures that mimic failures in upstream services. So with Istio, we have the ability to do that so that you can test your code and see what happens. This next feature, dynamic routing, is actually, it's also a really cool feature that we have. So let's talk about dynamic routing without Istio. Okay, one of the major challenges with management of your microservices is trying to understand how the services are composed and how they are connected, and how the different individual components operate from a global perspective, and then drilling down into particular detail. So besides the advantage of breaking down services into microservices, this paradigm also increases the complexity of securing them due to a shift of method calls via in-process communication into many separate network requests which need to be secured. And every new service you introduce needs to be protected from things like man-in-the-middle attacks and data leaks, managing access control, and audits, who's using those resources and when. Not forgetting the fact that each service can be written in different programming languages. A service mesh like Istio provides traffic control and communication security capabilities at the platform level, and it frees all of the application writers from those tasks, allowing them to focus on just core business logic. Now, with this dynamic routing, it gives us the ability to mimic or do some other scenarios. For example, one scenario that's very easy to do is what's called canary deployment. With Istio Service Mesh, you have the ability to dynamically route between microservices simply by configuring the system. Now in this scenario, you've actually got two microservices that are the same, but one's version 1 and the other's version 2. And with canary deployment, what we want to be able to do is to configure our system, maybe using a header or some other variable, so that requests that come in from specific locations, for example, are going to be routed to a specific service. So in this example, we have something that says anytime a request comes in from someone located in Boston, we want to automatically route them to version 2 of our service. And maybe there's going to be reason for that. Maybe there's special code that's written for Boston employees versus everyone else. And again, using this Envoy proxy, you don't have to change any code to make that happen. And at any point in time, you can actually just reconfigure it, redirect, maybe if there's a different scenario that gets implemented or incorporated into your system. Another scenario which we handle is called A/B testing. A/B testing is a method of comparing 2 versions of an application against each other to determine which one performs better. So with A/B testing, it's essentially an experiment where 2 or more variants of a page are shown to users at random, and then statistic information is used to determine which version performs better for a given goal. So in this example, you can see that what we've done is we have 2 versions of a service, and we've determined ahead of time that we want each service to get 50% of the traffic. And with that, we can again analyze tracing information, and we can determine which one performs better with the data that's being sent to it. And again, this is all handled through simply configuring and leveraging an Envoy proxy. Now, this last scenario is an interesting one, and that's what we call a dark launch. So the Istio service mesh can also be configured to allow traffic to be mirrored. So in this example, we've got version 1 of the code where 100% of the traffic is going to version 1, but we have a new version of the code that we want to be able to test with real data. So what we've done is we've deployed version 2, and we want to mirror traffic, everything that comes through to version 2. And in that process, we can actually test that version with actual data and to make sure that it does its desired functionality. Now, we also have the ability to do distributed tracing with a tool called Jaeger. And distributed tracing enables users to track a request through the mesh that's distributed across multiple services. This is going to allow a deeper understanding about request latency or serialization or parallelism. And it allows you to visualize it in this user interface. In fact, when I'm done speaking, we're going to demo several of these different components, and you're going to see exactly what it looks like when you look at it through the eyes of the service mesh. And last but not least is service mesh observability. And this is where the tool called Kiali comes into play. And what you can see on this screen is it's the series of microservices that have been created to aggregate and create an application. And again, during the demonstration, you're going to see this, but basically, as you look through each one of the different components, you can see, for example, multiple versions of a particular microservice that have been deployed. You can see the actual communication and how things are directed. So it gives a visual representation of the actual aggregated application that you've created. And there are different things you can look at. You can look at percentages, you can look at timing. You can actually basically pull this information and do a lot of great things with it. So with that, I'm going to pause and I'm going to let my colleague at Moser, Tom Lapp, take over the screen, and Tom's going to actually demonstrate to you the service mesh. Thanks again for your time and listening to my presentation. And again, we're going to hold questions at the end of the demonstration. So Tom, you're up. Tom, I don't know if you're on mute, but I don't hear anything.
Yes, we're having some issues, and Melinda's having to unmute us all manually.
There, I believe I have you unmuted now. I can hear you, Tom.
Yeah, I'm good. So, all right, thank you, Jim. Great overview of everything that that the service mesh has to offer. As I'm guessing you all are thinking, wow, this is a heck of a lot of information to take in, and there's certainly a lot of functionality that it does provide. So what we're going to do is we're just going to take a quick run through and demo a couple of these things that Jim talked about. We're not going to get to it all. It is, as I said, it is a lot. So we're going to take a look. We're going to run through a couple pieces of what is sort of an interactive lab or workshop that Red Hat has here for overviewing the service mesh. So we're going to just start by taking a look at the observability with Kiali. We're going to take a quick look at what we can see with the Jaeger open tracing. We're going to talk about and show an example with some routing inside of Service Mesh. And then also we're going to just take a look at some rate limiting also to see what we have. This interface is part of the workshop interface. It's based on a project called Jupyter Hub. It's really neat if you've ever done any of these before. It gives us a terminal that all runs in a web interface. It sends commands and does things for us. So it's, you know, when you do these workshops, it really lets you focus more on the content of the workshop rather than are you typing things correctly to issue commands. You know, these are the kind of things that, you know, if we have if there's a large group of interest, you know, from the attendees, you know, this is a workshop that we could run, you know, at a later date, either, you know, with a group of people from this, or if your company has a large enough group of people that are interested, we could, you know, spin this up and run one of these workshops for your individual company as well. So what we're going to do here is I probably am not going to read through a lot of this because Jim covered a lot of the content, the how and the what and the why and things. So what we're going to do is we're just going to get in it and take a look. So as you can see, I'm able to just send these commands right over. This is a quick, easy command that pops up a route that opens up our Kiali console. And is going to get us into being able to see some visualizations. So we're in that console. So what we're going to do now is we're going to go ahead and kick off this script right here. This is just going to sort of hit our service or our web application that we have deployed on this. And when we go back to the console, we'll kind of walk through that service and, you know, we'll show what we have. So what we are is we're in here, we're in our user tutorial. We want the versioned edge graph. We want to see request percentages. And let's see. There we go. All right. So here you can see this is very similar to the graph that you know, Jim showed on his presentation. What we have here is we have sort of a three microservice application. It's got a customer service, a preference service, and then a recommendation service. The services are kind of represented by these triangles here. The pods that back those services are represented by the squares. As you can see, for the customer service, we have one pod version 1 backing it. For the preference service, we also have one version 1 pod backing it. But for the recommendation service, you can see that we have 3 pods backing it. We have a version 1 pod, a version 2 pod, and a version 3 pod. You know, this is just showing that, you know, we can have lots of different pods of different versions that can back a single service. As you can see here from our traffic split, obviously we're coming 100% back to back through the first 2 because there's only a single place to route that traffic. But once we get to the recommendation service, you can see that we're splitting that traffic about a third, right? It's very close, and as it continually hits the service, we're continually round robining that and you know, splitting it out at a third, and a third. So this is the kind of visualization that you can get with, you know, with Kiali, with the service mesh that you'll look at. You can see we can drill down into individual services. You know, you can look at you know, HTTP requests or HTTP result codes, status codes, errors, things like that. All kinds of good information here that this is going to present to you. So that's kind of just a quick overview of the visualization that Kiali is going to give you. We'll come back and look at a couple of other things as we adjust some routes and some other different things. So let's see. So all right. So we've taken a look at that. All right. So what we're going to do now is we're going to hop in and take a quick look at Jaeger, which is the distributed tracing we're logged in here. Okay, so we're good. Sorry. So we're going to do that by popping over here onto the distributed tracing section of the console, and you can see, so if we're looking here, we get the ability to choose our services. We can look back at a certain time range, and we can see this whole service process and how everything comes in, where it's traversing each individual service, where it's how long those transactions are taking, and what the application is sort of waiting on. So this is you can see the overall time, right? And as we drill down, we get into the smaller and smaller pieces with the end-to-end. So this is really great to be able to look and see if you have an application that starts to respond slowly, that starts timing out. This is going to let you jump into the tracing and find out where your issue might lie. It's going to give you an opportunity to say, oh, look, microservice, that microservice C is, it's taking 4 times as long as we think it should. Did we introduce an error into our code? Is the database query it's making failing? Why is that returning so long? So it gives you a lot of good information to look, to start your research, as opposed to just guessing, why isn't my application responding as fast as it is. So you can really see what's going on behind the scenes of the service mesh. And so that's really just, all the instructions. So we're gonna stop that load there, and we're gonna move on to the next little section in this, which is routing in the service mesh. So with routing in the service mesh, what we're gonna do is we're gonna take a look at a couple of the things Jim was talking about, sort of things like canary deployments or preference-based routing, things like that, to your application services within the mesh. So let's see, make sure everything looks good. Okay, gateway setup, everything. You look good. So inside of that service mesh, right, we have a couple of ways to specify routing rules and the things that we can preference on, right? Routing to specific destinations, matching on the transport types, matching on specific headers or things like that. I think the kind of something that or location-based type things. We'll see, I think, a header example here down in the bottom of this. And then we also have different destination rules, which allow us to specify different policies as to where we want that traffic to go based on the sort of service selection. So what we're going to do is we're going to fire up a load generation script again, and we'll go back and take a look at our latest implementation of the graph. Now, as you can see, there's no traffic here because we're only looking at the last minute of traffic, and we had stopped the load generation script while we were looking at some of the other things at the end of that module. So now you can see we have some data populating in. It's coming in. We're updating every 15 seconds. And as you can see, we've got pretty dead on even balance here. About 33%, a third of all the traffic going to each one of our different back ends. So what we're going to do is we're going to add some weights here to the service mesh. And so we're going to add a couple of destination rules, and then we're going to put some weight to those. Again, this is what I like about this interface, this Jupyter Hub interface is, you know, they do show us what we're doing and everything, but I don't have to worry about typing it. It's all set and it's good. So that's adding the destination rule. Here, what we're going to do in the next part, now that we have the rule, we want to set up this virtual service, and this is where we're going to set up our weights. So as you can see here, for our recommendation, we're going to send to V1 at a weight of 80% of the traffic, and for our destination, for the recommendation of V2, we're going to route that to 20% of the traffic to the V2. So that file already exists. So what we're going to do is just go ahead and pop that over, and it's going to apply it for us. We'll go back to our Kiali interface, and we'll give it a minute. It's going to take a few rounds of traffic to start seeing the updated balance, but we should fairly quickly see this start to rebalance, and version 1 is going to go up. Version 2 is going to go down, and version 3 should end up eventually at 0. So as you can see, it's moving. Give it. So we're real close right now. We're almost at our 80% load or traffic rate on balance on routing to version 1, and about 20% down here routing to version 2, and version 3 is almost at 0. It's going to go to 0. So now we're even closer. It'll steady out, right? This is obviously all 80-20 rule is all over, you know, a longer term, right? So as that term gets longer, it'll get closer and closer to being right on as it routes, continues to make those decisions to route that traffic. So we can also modify all of that, change it up, and here we're going to switch this. We'll flip this. What we're going to do here is we're going to flip this from 80-20 to 20-80. So we're going to basically switch the weights, and now version 2 is going to get the majority of the traffic, and version 1 is going to get a minimal amount of the traffic. So this is this is sort of a canary deployment example. You bring a new version online, you route a small amount of the traffic to it to make sure that it responds correctly, that it doesn't generate any errors and things like that, and then you slowly ramp up the routing weight for the new version. And eventually you will just get to the point where you're routing 100% of all your traffic to your new version. So you can see this flips pretty quickly. We're updating every 15 seconds here, and the traffic generation is almost flipped completely from the 80-20 to 20-80. So it's it's pretty easy to maintain, not too much. So we'll go ahead and clean this one up. And after we do that, we should see the traffic start to rebalance. And it's coming in. So version 3 is starting to get some traffic, and it'll come back up. Okay, so canary release, right? So we just kind of talked to this. This is very similar to what we're doing. Or what we talked about based on weight. Here, this example is going to do it with a user location header. What we're going to look for is a header in the request that is going to be the Boston in this case, and we're going to route all of those Boston requests to version 2, and we're going to route everybody else to the version 1 of the application. So we'll go ahead and pop this in, and that's going to update those wait rules, that virtual service that is adding the routes and the configuration. And then we're also so what we're going to do here is now we're going to watch this script, and as we can see, everything's coming from version 1 because our rules are going to route everything that doesn't contain the header Boston into version 1. And this example script that we're running here does not contain that. So if we kill that, and then we up here, so this, excuse me, sorry. So if we run this, you can see we're running a simple curl with a user location header of Boston to our ingress gateway, which is the ingress for that URL for that that application, and you can see we are getting our recommendation back from our V2 endpoint. Okay, so that's another example of a canary deployment based on a different a selection factor, right? You can either base it just solely on routing percentages of traffic. You can look for certain headers. If you want to, route your Firefox users, website visitors, or application visitors based on their Firefox header, you can do that. You could send your Google Chrome users to a different route and a different application backend. Just all kinds of options that you have there. Let's go ahead and clean this one up. And we got a few minutes left here, so I think I can squeeze in taking a look at rate limiting policies. So this is, I think Jim talked about, this is kind of a way to, maybe deal with denial of service type things or overly aggressive apps. Maybe, just to keep your application, help try and keep your application stable if maybe something, outside or on the other end goes a little crazy and starts just banging away too hard at yours. So we'll go ahead and get this all set up. All right, everything looks good. So what we're going to have to do is we're going to have to set up a couple of different pieces for this, destination rules and some recommendation for the recommendation service. Okay, so we have a destination rule in there already from probably one of the previous events. And now what we're going to do is we're going to add in a rate limit for version 2 of the service. So we've added a handful of different things here. You can see we have a quota handler, a request count quota, request count object, couple of different things, quotas that have all been created. And so what we're looking at here is this big old chunk of YAML that went in to create all this. And what we're really looking at here is kind of this override right here, is that for the destination of recommendation, we're going to have a 5-second duration with a max of this one connection. And then we're going to, down here, where is it? This is where we bind it, and we bind it in to our service, our recommendation service, so that everything handles that. So we'll go ahead and run some tests, and as you can see, so this test is going to try and hit that. And as you can see, so once we make 6 connections, we time out. And I think actually this must be bound. I might have read that wrong. This must be bound to all of the entire recommendation service, not just version 1 or version 2 or in that. So as you can see, right, again, all right, we hit the bang, 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 version 1, version 2, version 3, and then we get, you know, this resource exhausted quota error. Right. So if we go take a look in Kiali now, you can see we've got some errors. You can see we've gone from green to some red here. And you can see that we're equally weighting our distribution to version 1, version 2, and version 3. And then we're starting to see some 500 errors that are coming in, HTTP errors in our request. So, you know, this is the visibility that Kiali is going to give you into what's going on in your service mesh. Right, so that's just a quick look at dealing with things like that, the rate limiting and other things, quotas and things. Go ahead and clean that up, and looking good. We're not generating any traffic, so as you can see, we've gone back to a sort of steady state. So that's a quick overview of some of the things we talked about, some of the things that you can do with Service Mesh, the visibility that it's going to give you into your Service Mesh and your microservices. So with that, I will hand this back to Melinda.
Yep, I'm here. So thank you all. Oh, Jim. Yes, I will unmute Jim. Thank you all for coming. If anyone has any questions, type it into the box and our experts can try to answer them for you or get more information for you. Thanks everyone for coming. If there is nothing else, you can leave, but definitely we'll stick around for a few minutes for you to type in questions. We will be sending out a follow-up email with the recording. And so if you want to go back and watch any part of it, and we'll also send some information about other webinars we have going on. And in the next week or so, you should receive an email from DoorDash with a coupon code as a thanks for coming today. So look for that in your email. It will be from DoorDash, not from Moser. They send it out as a group. So are there any questions or anything you'd like to see or go more deeply into right now? All right, well, thank you everyone very much for coming, and look forward to the follow-up email, and thank you so much.